This is an introduction to the Faraday rotation lab for the intermediate lab in spring of 2017. The student learning outcomes for the lab are to experience what happens when a magnetic field is exerted on a dielectric and see what happens to the polarization of the light. Also to practice making a measurement in multiple ways so that you can get good results. To think about how to make measurements in more than one way. There are two lab objectives. The first is to test the experimental apparatus by plotting the light transmission versus angle of an analyzer, and to show that it follows Malice's law, which says that I equals I naught cosine squared of delta theta. The second objective is to find the Verdet constant of a sample that we have, which is a rod made of SF59 shot flint glass. The rod's 10 centimeters long, 5 millimeters in diameter, and you will use the information in this video as well as in the pre-lab and the additional literature in order to make the best value, the best measurement that you can. All right, so very simply, Faraday rotation is a rotation of light due to a magnetic field. This picture shows, and I'll repeat this picture many times because it's just a simple depiction of Faraday rotation. It shows that if we have an electric field that's polarized as on the left here, vertically, linearly polarized, and it enters a material that has that's a dielectric. If we exert a magnetic field on this material in the direction shown, the light will rotate in a particular direction based on that magnetic field, and it will come out at a different linear polarization angle. I'm going to say something pretty important here that you'll follow up with the pre-lab question. Notice that you could use a right-hand rule to determine the way that the light goes. So if you put your thumb in the direction of the magnetic field, towards the right here, your fingers are going to be curling in the direction of rotation of the light. And this is true for a positive, a material with a positive Verdet constant. So we'll come back to that, but I wanted to mention it at least once here. So what the Faraday rotation is the rotation of the plane of polarization, we just said, of a linearly polarized wave. And what's happening is a magnetic field going through a dielectric makes it become circularly birefringent. So what does that mean? Circularly birefringent means that there are different indices of refraction for right circularly polarized, or RCP, and left circularly polarized light. So when we start with a linearly polarized wave, what we realize is that it can actually be broken up into right circular and left circularly polarized light, as we're going to see on the next slide. So here, let's write right circular polarization, and it would be something like an X term along the I hat direction with some phase, and a Y term along the J hat direction with a phase that's different by pi over 2. So this last little phase term here gives us circular polarization. And in this case, this would be right circularly polarized. Now, left circularly polarized has the opposite phase. We could also move that opposite phase out to an I term in the exponent outside of the cosine term. It becomes a minus outside of the cosine term. And what's interesting about that is that when we add those two fields, the right circularly polarized field and the left circularly polarized field, let's see what happens. If we add the first term here, and for the left circular polarization, add the way it's written the second time, the J hat terms just disappear, and we're left with only the X term, which is horizontally polarized. So it's linearly polarized in a horizontal direction. If we subtract them, we get an electric field that's linearly polarized in the vertical direction. So circularly polarized, right and left circularly polarized light will add together to give us linearly polarized light. All right, so let's come back to what we were saying. A linearly polarized wave, which can be decomposed into right circular and left circular polarized light, will experience a rotation due to the birefringence, due to a relative phase between the right and left circularly polarized lights. So if you put your hands together and you rotate them relative to each other, you will get a different linear polarization. Again, if we start with our right circular polarized light and then our left circular polarization has an extra phase term, we're just writing all the phases as the cosine instead of an exponential. And we add those together, we'll get something a little bit different. We get a term that's not quite along the I hat direction and a term that's not quite along the j hat direction, and that would be linearly polarized at some angle delta phi. Okay, so back again to our description. We start with the linearly polarized wave, and it's broken up into right circularly polarized and left circularly polarized light. Each experience a different phase, and therefore the linearly polarized light is rotated. The actual angle of rotation of the wave is given by this expression. It says delta theta, the angle with which the wave is rotated. In this picture, it would be a beta, so that's the same as our delta theta, is equal to V times delta B times L. So clearly it relates to magnetic field, and the V is called the Verdet constant, and L is the length of the material. The area of the material doesn't matter. So again, the polarization rotation is proportional to the magnetic field, and its proportionality is given by the Verdet constant and the length of the material. All right, so on to our first lab objective. The first lab objective is to understand polarization, polarizers, and analyzers. So what you're going to do is start with a polarizer and measure the amount of light going through a polarizer and then an analyzer when you rotate the analyzer. So if the polarizer and analyzer were in the same direction, in other words, if theta was equal to 0, you would expect that you would get the maximum amount of light through. And if the analyzer is then rotated, you expect that you would get a different amount of light through. And you're going to plot this, plot the transmitted light, so plot I over I naught versus delta theta. So when you plot I over I naught versus delta theta, you should see that it goes as cosine squared. So test that out for the first objective. And then for the second objective, you're going to find the Verdet constant. So this seems pretty straightforward. I mean, basically, there's our material, and there are a couple ways of doing it, and I'm going to suggest two different ways. First way is to make your polarizer and your analyzer crossed with each other. In other words, set your analyzer so you get the minimum amount of light. We dealt with this with the polarization lab. Then do something that will give you a plot of rotation versus magnetic field. The pre-lab video, the live video, helps a little bit to see how you can use the measurement on a scope and on the photodiode to acquire this information. So what will it look like while you gather your data? One way of doing this that I'd suggest, and I suggest doing more than one technique, one way of doing this is to first rotate your analyzer to get the lowest photodiode voltage, in other words, for the best extinction, and then change the magnetic field, rotate again, change the magnetic field, rotate again, and record your analyzer angle at for each magnetic field. You can then plot analyzer rotation versus magnetic field, and that's a direct plot of delta theta versus B. Remember that you're actually measuring the current, but we'll deal with that. Another technique is to record the transmission voltage at each magnetic field. The transmission voltage is going to be proportional to the intensity. So we can convert that to an angle measurement using Malice's law, where I over I naught is the current intensity divided by the maximum intensity, or whatever you want to use to normalize your intensity. So when you measure the transmission voltage, that is the same thing as measuring the intensity of the light. For these two techniques, try it again with your polarizer and your analyzer at 45 degrees relative to each other. This gives you a photodiode signal that's not minimum, but somewhere in the middle, and your response will be a little bit different. So see which technique works best and gives you the best result. All right, so here you'll see the equipment for the experiment. This video describes the equipment for the Faraday rotation experiment. So the actual setup is pretty simple. There are very few parts to it. There's a coil of wire which will create the magnetic field for the experiment. And within this coil of wire, there are two rods of a particular material that will change as you apply a magnetic field to it. So to get started, we'll talk about the other pieces as we go along. To get started, we're going to turn on a little laser here. The laser is connected to a power supply through this audio amplifier. So we step around, we plug in the audio amplifier, and that turns on the laser. So we now have a laser coming through this tube. You can work on checking the alignment, that it's making it through the material inside the tube, inside the coil of wire. And then the next piece is we have a polarizer. This is just a linear polarizer in a rotation mount. It's not set in the mount at any particular orientation. And then next we have a photodiode, and the photodiode is how we're going to measure what's happening in the experiment. So the photodiode we watch in two ways. We can either look at it on the oscilloscope or on a multimeter. On the scope, connect the photodiode, our signal disappeared, so your first job will be to find the signal again. And if you need help with that, of course, just ask. So the signal is now at 0 on a 2 millivolt scale. All right. So what we're going to do is watch what happens as we apply a magnetic field to the coil. And again, we can watch here. As the amount of light on that photodiode changes, the signal will change. And one way to do this experiment is to minimize the amount of light, set that to the 0 position on the scope. Again, you can check minimizing. And then when you apply a magnetic field, does the amount of light going through the polarizer change? And the answer will be yes. So here we just have a power switch. You can check that all the knobs are turned down. Turn the power supply on. Turn up the voltage a little bit. And then what you're interested in is the current. So you can control the current. Turn up the current to something like a volt, or like an amp. And you'll notice here that the signal has changed. So that's what you want to see happen first. That means your experiment, your equipment is working. When you change the magnetic field, the signal going through the polarizer will change. And at that point, you're ready to go. You know how to rotate the polarizer to let different polarizations through. You know how to turn on and off the magnetic field by changing the current. And you know how to look at the signal on an oscilloscope. If you would prefer to use a multimeter instead, you can just, or try both ways, you could just take your BNC and connect it to the multimeter and look at the multimeter scale. The signal's quite small, so you want to use a low scale. So that's all. The pre-lab questions are to look up some Verdet constants. Just do a little bit of searching wherever you'd like to look for different materials and Verdet constants and write them down. And get an idea of what you think you should get for the Verdet constant of the shot flint glass. And for the third question, Given that the Verdet constant is positive, sketch what's going to happen as the laser passes through the material. So what direction of rotation do you expect as the laser passes through the material? And that's it, the usual getting started. There will be several questions that you'll have as you do the lab and as you read the additional materials in the lab handout. So continue to think about it and be ready to go for lab.